So the fifth lesson of the organic synthesis topic is going to look at the other two addition reaction mechanisms. So we've got our acid catalyzed hydration, which we're going to start with, and then our halogenation, which we are going to look at after this one here. Okay, so our acid catalyzed hydration. So it says a hydration reaction will produce one product with symmetrical alkenes and two products with non-symmetrical alkenes. The acid, which is all acids contain H plus ions, so we can see the H plus catalyzed hydration reaction is a three-step process and proceeds via a carbocation intermediate. So what I'm going to start by doing is drawing in an alkene. So I'm going to use methylpropene. And the first step in this reaction involves the H plus catalyst. So I'm going to draw in my H plus ion as well. So what will happen here is the electrons in the pi bond. Now remember, in a carbon-to-carbon double bond, you've got one sigma bond, an end-on overlap, and one pi bond, which is a sideways overlap. The electrons in the sideways overlap kind of occupy the space where I put those kind of like two blue kind of lines or two blue marks. So because the electrons are kind of in that sort of area there, it means that they are able to attack things which are positively charged. So they are able to attack the positively charged hydrogen ion. So that's exactly what I'm going to start with doing. So I'm going to start my curly arrow at the carbon-to-carbon double bond, and I'm going to end the curly arrow where I'm going to make the new bond between the carbon and the hydrogen. Now for this one here, I'm just going to go with the Markovnikov product. So I'm going to have the bond between that hydrogen and the carbon forming on the carbon on the left hand side, which is the carbon with the most hydrogens already attached. So that's going to be my curly arrow there. And what that is going to do is it's going to form our carbocation intermediate. So the carbon-to-carbon double bond has broken. The electrons that were in that bond are now bonding to our hydrogen. And our carbon in the middle has lost the electron that it donated to the carbon-to-carbon double bond. So it's now positively charged because it's one electron short. Okay. So I'm just going to put a wee explanation underneath. So we'll say the C2H4 nucleophile first attacks the H plus ion catalyst, creating a carbocation intermediate. So we can see that's exactly what we've got in that first step. So the electrons in the pi bond, which is what makes alkenes a nucleophile, the presence of those electrons in the pi bond, they attack the positively charged hydrogen ion catalyst and gives us our carbocation intermediate. Right, so in step 2, water, now this is a hydration reaction, so it also involves water. So the water will then be attacked by, the carbocation intermediate will then be attacked by water. Now water is also a nucleophile because it has two non-bonding pairs of electrons. And one of the things that makes something a nucleophile is either presence of electrons in a pi bond, or a negative charge, or the presence of one or more non-bonding pairs of electrons. So I'm going to take my carbocation intermediate, and I'm going to draw in a water molecule. Now, on the water molecule, what I'm going to do is I'm going to pop the lone pairs on the water so that we can see them. There and there. And one of those lone pairs is going to attack the positively charged carbocation, forming a bond between the entire water molecule and the carbon with the positive charge. So I'm going to start my curly arrow where one of the lone pairs of electrons is on the oxygen, and I'm going to end that where I'm going to put the bond between the carbon and the water. So we'll end up with something that looks like this. Okay, so what we've got is we've got a second intermediate. Now this intermediate that I've drawn on the right hand side of my reaction arrow here is called a protonated alcohol. It's an alcohol that has an extra H plus ion on it. So that's exactly what we've got. We've got an OH group, but there's an extra H plus ion on it. So that's a protonated alcohol. So we're just going to say the carbocation, which I'm just going to write as the positively charged carbon, is then attacked by the nucleophilic H2O, forming a protonated alcohol. So I'll just give you a little moment to make sure you've got that all copied in. And then we have our third and final step, which is to regenerate the hydrogen ion catalyst and form our alcohol. So that's exactly what's going to happen in the final step. So I'm going to take my protonated alcohol, and what's going to happen is the electrons in one of the oxygen to hydrogen bonds, it doesn't matter which one, both of those electrons are going to push onto the oxygen, which will break that bond and leave the hydrogen separate as an ion, because one of those electrons in that bond belong to the hydrogen, one belong to the oxygen, and they are both going to push back onto the oxygen. So I'm going to start my curly arrow at that bond, and I'm going to end it at the oxygen because the electrons are going back onto that oxygen. So we end up with our alcohol, and we also regenerate our hydrogen ion catalyst. So the hydrogen ion that began the reaction, that catalyzed it at the start, is replaced with a different hydrogen. So it's not the same hydrogen ion that we get back. It's a different one, but as long as the catalyst is regenerated, we can still say that it's a hydrogen ion catalyst. It doesn't matter if it's a different hydrogen. So then a quick explanation for that. So we're just going to say the H plus ion catalyst is reformed and an alcohol is produced. So again, I'll give you a wee moment on that step there. Okay, so some similarities in this addition reaction mechanism to the addition reaction mechanism for a hydrohalogenation. So they both use a carbocation intermediate, but because this reaction here first involves a catalyst, so the nucleophile attacks that H plus ion catalyst to begin with. That's the kind of key difference. So it doesn't start by attacking the water. It starts by attacking the H plus ion catalyst. That forms the carbocation. And then the water, which is itself a nucleophile, it then attacks the positively charged carbon. And then we reform our catalyst like so. So that one's definitely a bit more involved and probably a wee bit trickier than the hydrohalogenation. But they do use the same intermediate, the carbocation. Now I'm going to go up to the first addition reaction mechanism that was mentioned in the booklet, which is halogenation. Now the reason why I have left this one to the end is because it's probably the trickiest in terms of drawing it, just because the cyclic intermediate's a wee bit tricky to draw sometimes. So for a halogenation, we will always produce just one product, and the mechanism for a halogenation reaction is a two-step process and proceeds via a cyclic intermediate. So this one definitely has the most in way of curly arrows. So we'll have a wee look at this one here. Now, this is a very, very different set of circumstances that leads to this reaction, because what I'm going to do is I'm just going to take the most basic of alkenes. I'm just going to look at ethene just to try and keep things as simple as possible. Now, if ethene is reacting with a halogen, halogens, remember, are diatomic and they're non-polar. So if we have a non-polar molecule, there's nothing for the electrons in the pi bond to attack. They need something with a positive charge or even a partial positive charge to attack. And it does really go down to that opposites attract. So because we've got areas of electron density around that carbon-to-carbon double bond, they need something that's positively charged, like a hydrogen ion, or something with a partial positive charge. So like the positive end of a polar molecule to be able to attack. Now, halogens, like fluorine, I'm going to use fluorine for this one. Fluorine doesn't have a polar side because it's not a polar molecule. So what will happen is the fluorine molecule is actually going to get very close to the double bond. And as that fluorine molecule gets close to the double bond, the electrons in the pi bond cause the electrons in the fluorine bond to be repelled. So the electrons in the fluorine to fluorine bond actually end up closer to the fluorine, which is furthest away from the electrons in that pi bond. So in effect, the molecule polarizes, so it becomes polar. So we get a slightly positively charged fluorine, the one that's closest to that double bond, and then we get a slightly negatively charged fluorine because the electrons in that pi bond are pushing the electrons in our fluorine to fluorine bond further away because electrons are highly repulsive. Now I'm going to write a wee kind of passage or say a couple of sentences about that process once I've showed you what the intermediate looks like and how we get there with curly arrows. Okay, so what will happen is, and just to make this a little bit easier, what I'm going to do is I'm going to pop one of the lone pairs on the fluorine. So each of the fluorine atoms there has 3 lone pairs. And I'm just going to draw one of them on and you'll see why I've done that in a little moment. So we're going to start with the attack from the electrons in the pi bond. So what's going to happen is we're starting our curly arrow at the carbon-to-carbon double bond, and we are going to end that curly arrow in the space where we're going to be drawing a new bond between the carbon and the fluorine. What's also going to happen is because this fluorine atom is really close to the carbons, one of the lone pairs on the fluorine is going to form a bond to the other carbon atom. And then the electrons in the shared pair of the fluorine to fluorine are both going to move on to the delta negative fluorine. So if we look at what that's actually going to look like in terms of a product, so I'm breaking the carbon-to-carbon double bond. I'm keeping my hydrogens that are already there. Now I'm making a new red bond because I'm going to say that the electrons in that pi bond are the red electrons. So that's going to be a bond between the carbon and the fluorine. The fluorines then donated a lone pair to form a bond here. So this is our cyclic intermediate. So it is like a kind of ring shape. So that's cyclic. So that's our cyclic intermediate. Because the fluorine has donated a pair of electrons to the carbon to fluorine bond, that makes the fluorine have a positive charge. And then our other fluorine will form an F negative ion like so. Okay, so quite tricky in terms of the arrows there. But if you can remember the shape of the cyclic intermediate, you can kind of put the arrows where the bonds are going to go and you can kind of get away with it in that respect. So what I'm going to do is just write in a wee passage explaining kind of what's happening there. So we'll say, as the nonpolar F2 molecule approaches the carbon-to-carbon double bond, the pi electrons in the double bond cause the electrons in the fluorine to fluorine bond to be repelled. This causes the F2 molecule to be polarized, creating a delta positive charge that the C2H4 nucleophile can attack. Okay. And again, as I was saying, if there is no positive charge or delta positive charge, then the electrons in the pi bond have nothing to attack and the reaction simply doesn't take place. So what will happen is, because those electrons in the fluorine to fluorine bond get repulsed or repelled, we end up with that molecule becoming polarized, which creates that slightly positive charge, which then enables the nucleophile, the C2H4, to actually attack that molecule and allows the reaction to take place. I'll give you guys a wee minute just getting that copied in, and then I'll show you step 2. Now, just as a kind of other wee aside, sometimes you'll see the positive charge on the fluorine drawn where I drew it there. Other times you'll see the positive charge on the fluorine drawn in the middle there. It's the same thing. Just depends on the diagram at the time. So you might see both, but ultimately it makes no difference. Okay. Right, let's go on to step 2. So I'm going to start with my carbocation intermediate. It's not my carbocation intermediate, sorry, I'm starting with my cyclic intermediate. Right, so what will then happen is the negatively charged fluoride ion that we created in the first step, that is then able to attack this molecule. Now I'll show you what happens in the attack. So the key thing is that fluorine ion attacks the molecule from the back, okay? So what will happen is this fluoride ion will attack either one of the carbons. It really doesn't matter which one you do. So I'm going to attack the carbon on the right hand side. So I'm starting my curly arrow where the non-bonding pairs of electrons are on my fluoride ion, and I'm ending the curly arrow in the space where I'm going to be drawing a new carbon to fluorine bond. What will then happen is that will then cause the bond between the carbon where you're forming the new bond and the carbon to fluorine bond in that cyclic intermediate that already exists. That bond will then kick off. So what we'll do is we'll start our second curly arrow on the carbon to fluorine bond in the intermediate, and we're going to put those electrons in that bond back onto the fluorine, which will break that bond and leave just the blue carbon to fluorine bond on that side there. like so. And that's going to be our product there. So we'll say the F minus ion can then attack the back of the cyclic intermediate. Okay, so that is us done with our addition reaction mechanisms. So there is an exercise on alkenes, exercise 2.9, that has now gone live. So you can use the remainder of the lesson today to work through that exercise, and it is due for tomorrow, I think at 4 o'clock. So you can use any of your kind of free periods the rest of today and tomorrow just to get that exercise finished. So the exercise is all on alkenes. So it will be looking at addition reactions following Markovnikov's rule, minor and major products, and also giving you a chance to have a wee look at drawing out some of these addition reaction mechanisms. Okay, so basically do the best you can with the reaction mechanisms. They're not easy. They're one of the hardest parts of the advanced higher course, not just one of the hardest parts of the synthesis topic. So just take your time with them. Follow the 3 examples that I've given you, and if you've got any questions, then please just let me know and I will do my very best to help you out. So if you've got any questions, I'm going to stop the recording just now